let's just start out. I don't know if Carl was going to say something. So
That's okay.
All right, we'll just do it.
No pressure. No pressure.
I'm Mike, and this is Brian. We'll talk in a second. We're both on the data science team here. And today we want to talk to you a little bit about a framework we built in-house to solve some problems that we had in sort of getting recommender systems and models into production. First of all, we're just going to tell you a little bit about data science at WW, the new Weight Watchers. We're going to talk about the problems that we had, and maybe there's similar problems to things that you guys have encountered or will encounter, so it might be helpful. Talk about the solution that we put together to try to solve those problems, and then Brian's going to give you an example of an actual implementation that we put together that is like a product that we have now in our apps. So WW is the new Weight Watchers, and kind of our purpose is to inspire healthy habits for life, real life. And the idea behind that is that we're going a little bit beyond what the brand has really excelled at, and it's been really encouraging weight loss for members and giving tools to help with weight loss. But we're moving to more holistic view that helps people on their entire wellness journeys, including activity and sort of restaurant selection and food selection, and some of those things we're going to talk to you today about. So it's a data-driven application. Most members interact through WW through the application itself, instead of the meetings that you might be familiar with. There's still about 25% of members that go to the meetings, but a lot of the people actually use the application as their primary sort of way that they see us and work with us. And there's a lot of sort of features that surprise people if they're unfamiliar with it. So first of all, there's a pretty active member social network. It gets about 10,000 posts an hour. It's most similar to Instagram. People post videos, people post images, they have comments, they can like each other. And we have several projects that kind of work with that team. There's activity and food tracking, which is kind of a core piece of the app. A lot of that involves search, which is pretty closely related to recommender systems in terms of being able to find the appropriate foods for someone when they want to track their foods or understand the nutritional value of their foods. There's weight progress and goals and tracking and things that people can see their progress with. And finally, something that Brian's going to talk to you about, there's a recipe and food database that allows people to find recipes that they want and foods that are going to be perfect for them given their implicit taste preferences. Some projects that we've worked on, just so that you guys have a holistic view of the data science team. On the growth side, we've kind of built back-end models that I think most data science teams are familiar with: churn models, return models, LTV models, a concept called single member view where we cluster members together across memberships, even if they sign up with different information. On the program side, these are kind of core data products. These are like our recipe recommendations, similar recipes, composite food ontology, where we break food strings into the composite food items that they consist of. So if someone tracks like coffee with 2% milk, we need to be able to understand from that string that, that constitutes coffee as a main item and 2% milk is like a sub item. And that metadata is a project that we're working on. On the social networking side, we build personalized feeds. We have a groups search, which works just like Facebook groups, where you can find posts that are like in a narrow range of subjects. And we're also working on a who to follow recommender so that you can learn who people are that other members that you're likely to follow. And what we're mostly going to talk about today is on the infrastructure side. We build APIs, so we're kind of the full stack data science team. And we built infrastructure to help us get those APIs out quicker, which we're calling Primrose, and that's what we're going to talk about today. We're a new team, so we've only been here for a year, and a lot of those projects that I said have kind of been things that we've been tasked with sort of getting out for the first time in the organization. So the organization in general doesn't have a ton of experience working with machine learning. So for us, part of our goal was, as we grew as a team and as we brought more and more people on the team, was to be able to do it scalably and be able to do it in a way so that all of the data scientists can share work from each other. And when someone does one thing for one project, ideally another person isn't going to have to do that same thing for a project. And that was sort of part of the impetus for us to put together a framework, and part of the reason why we decided to kind of try to productionalize and abstract a lot of the work that we were doing so we could reuse it in what we're about to explain. Also, we're hiring in both Toronto and New York, so if any of this looks interesting to you guys, please talk to me after. So some challenges that we had at WW were really, we could categorize in 3 areas where we really, if we were taking stock of everything that would make a good recommender system here. First of all, we had a lot of requirements for batch jobs that would need to run maybe like once an hour or at the very least once a day. And a lot of sort of larger scale technologies like Airflow had a full serialization step every single time data was being read in a process. For us, that wasn't really appropriate, especially since the data that we were working with was usually around a few hundred gigabytes. So we could run everything easily on one node, but we were sort of being hit with huge serialization costs every single time we needed to do an operation. So we wanted to basically keep all of our data in memory, and we wanted to run everything on one node. Our second process was that we didn't really have an operational cache as like an engineering organization here. So for readily available features that you might want for a recommender system or a model, that stuff wasn't available to us right away. We've only been here for a year. We weren't going to re-engineer the entire architecture of the whole application. So for us, that meant that we wanted something that would work well with batch processing, and we wanted something that would work well in like the Kubernetes ecosystem, because there are already a lot of options here to deploy jobs, to deploy apps all through Kubernetes. So for us, that was an important requirement. And the third and maybe the biggest requirement was that we wanted really easy onboarding for new data scientists. We wanted to be able to take data scientists who hadn't necessarily made production code, people who had mostly worked in notebooks, and give them a way that they could sort of write their own production code. And we wanted to work in a mono repo for that same reason, so we could have easy PRs, keep track of everything going on. And we wanted a configuration as code concept. So when we move something into production, we can actually just do small configuration changes to sort of track the results. So we built a framework to sort of solve our challenges. After sort of looking through a lot of different options that existed, we decided that A, there wasn't anything that sort of perfectly suited our needs, and B, it might be kind of fun to build a framework so that we can kind of learn as a team and think about abstracting concepts in a way that I think ends up making your work better as you do it. And one final thing, we're open sourcing the framework as well. So this is something that's coming soon, and we'll have the link at the end. But we still have to go through legal and all the stuff that pertains to that. But hopefully one day this might be something helpful for others in the community as well. So the name of the framework is Primrose, and it's just a framework for simple, quick modeling deployments. And Primrose stands for Production and Memory Solution. Don't think about that too much. And it's a framework for solving our most common use case, which was caching batch predictions with machine learning engineering baked in. And to sort of solve our three problems on the data science side, the solution is totally Python-based, and it's an in-memory DAG runner. So you guys might be familiar with DAGs if you use Airflow, but I'll talk about it in a moment. And there's no serialization between the steps. On the infrastructure side, everything runs with configuration as code. So basically, you can have one container, and you can run all of your models in it. You can run a churn model. You can run a food recommender. You can run a social media recommender. All of it runs from the same code base. And on the people side, we've abstracted a lot of the ML and sort of recommender concepts. So it's easy to extend, and it basically helps our data scientists think of everything they do in like a modular way. And they can extend it if they need something or reuse something if it already exists. So Primrose jobs are executed as directed acyclic graphs, which is something that I think is pretty common in like the data infrastructure world. But these run purely in Python, and all of our jobs are partitioned into like these small nodes, which again, for writing code and writing jobs and writing things that need to be done repeatedly, it's a lot easier to sort of compartmentalize what you're doing and abstract it. It's very, very flexible. You can run any Python anywhere, any library that you might want to use. So, you can use TensorFlow, you can use any sort of neural net framework you want, or you could use simpler stuff like sklearn. All that stuff's sort of up to the user. And you can make pretty complex architectures in terms of reading data from multiple sources, writing data to multiple sources, reading and writing to caches. All that kind of stuff can be built into the DAG. And so when it runs, the convenient part is that data is ported from node to node in an internal data object. So if you're writing a node that's a model, the object that's given to you when you write that understands that I'm data for this model, and upstream there was information that was given to me that eventually flows into you, and it will all be present at that model. So it makes it really easy to write for a single model, using all of the information that you expect to be there will be there at runtime. And the DAGs are composed of implementation agnostic nodes. So what we've done is we've tried to abstract concepts that were that we were sort of seeing a lot. We have an abstract reader, abstract pipeline, model, post-processes, writer, and a success as a concept. But this is totally extendable. You could add more of these abstract classes if you want. It's just that all of them need to inherit from the node structure so that they know that they can be run in this graph. And then we're able to actually build implementations of each of these readers and pipelines that fit our needs. So again, the nice thing about this is that you can write anything that you might want, and you can choose any Python framework that you'd like for this. And that includes different data sources, different frameworks, different cloud infrastructures. We've gotten a lot of use out of this because we're on Google Cloud, and we've wrote like a BigQuery tool, and now that everyone's project can use that same tool to read in data. And the other cool thing about it from a deployment standpoint is it looks just like a job that runs in a container. So we have a large data lake here. Again, everything's done in batch jobs. And what we're able to do is just deploy the same container, and we can run arbitrary number of instances that just get a different configuration file each. And the configuration file defines everything. When you write a configuration file, Brian will show you in a moment, it registers all of the classes that you might need or that you've written, and it builds the whole graph and runs it for you. So there's no need to, you don't need to worry about all of your requirements or anything. The same exact container runs all of your jobs. And finally, like our case here, basically all of these have ways to write into prediction caching layers, and we write APIs on top of that prediction caching layer. So that gives us like really, really high throughput because everything is cached all the time. And it's really easy for us to deploy because we're just pushing out containers that run in batch jobs. And yeah, not to harp on this too much, but basically one of the key things that makes this easy to deploy is that everything is done through configuration as code. So whether you're doing a recipe recommender, churn model, connect feed, it's just a different JSON object that you'll write. Obviously, the first time you write it, you'll need to write some new nodes if it's new stuff that you haven't worked with previously. But beyond that, you just write a JSON that specifies your, where you want to read from and what you want to write to, and what depends in your DAG structure, what nodes depend on what other nodes. They go into a Primrose container, and then you literally achieve success, fame, and money with no other work at all. And that's exactly what it's been for us. So it's helped our team develop production models pretty easily. In terms of other places that I've worked, I think that we've gotten a lot done in the last year. We onboarded 6 members. Everyone's working in the framework at this point. And we have 3 models in production and 3 production recommenders right now, one of which Brian will talk to you about. So it's not a tool for necessarily the largest scale systems, one of which I think Yuri is going to talk about in a little bit. But what this does do is for things that are several hundred gigabytes in size, it gives you a really convenient way to keep track of your deployments and to have a really nice shareable infrastructure among data scientists. So next, Brian's going to talk to you about how we actually use this in practice.
So I'm going to try to connect this phone so I can just show something in the app real quick. We have the 646. Just connecting to Zoom. All right, there I am. Second. I'm going to stop sharing. And here we go. We're in? All right, cool. All right, so as you know, if you're trying to lose weight, you got to watch what you eat. So at Weight Watchers, food is very central to the core of our product. So as soon as you log into the app, you get your home screen where you see your daily points remaining. We use that to make sure you stay under a daily recommended budget to help you lose weight. And once you scroll past our ad asking you to have people sign up for Weight Watchers, you immediately get to food carousel. We also have a lot of other food carousels in the app. So if we go down to our Explore Recipes page, we'll see that same carousel again at the top, but then we'll have all these like curated lists of different recipes that are grouped by some category. So from the C, popular, lemon love, spring greens. So here at Weight Watchers, all these previously were kind of created by content curation teams. It's a lot of work to put together a new collection of recipes. So it's really a prime example of where data science can have a really big impact on our product. All right, so now I'm gonna stop casting this. I won't cast here. All right, cool. All right, that's the backup videos. All right, so one of our core tenets is that we know you and we meet you where you are. So all our members are tracking everything they eat. So in the hypothetical person here, they've tracked coffee and croissant for breakfast, fish tacos and apple for lunch, and a Cobb salad for dinner. Then they got some pasta and some ice cream. So maybe it was their cheat day or something. But we want to make sure that we're recommending to people things that they like to eat based on their previous behavior, and also maybe not recommending them ice cream if they don't have any points left to eat ice cream at the end of the day, so that they are achieving their healthy goals. So we want to personalize your experience using your data. So I'm going to talk about some simple limitations of recipe recommenders that we have and explain how we kind of put those into the DAG Primrose framework and how we deploy them. So on one hand, we have similar recipes. So, you click on a recipe, you're looking at the ingredients. If you scroll down to the bottom of the page, past how to make it, you want to see a carousel of, similar recipes to that recipe you're looking at, other things you might want to eat because you clicked on that first recipe. So that's one recipe recommender I'll call similar recipes. And then we have dinner recommendations. So, because you've been tracking chicken fried steak, we're going to recommend to you, stir-fried chili mango chicken with peppers. And because you track some other thing, we're going to put together this carousel of things that are related to things you've already tracked. And that's kind of how the dinner recommender works, and I'll explain that in a little bit more detail soon. So we're just going to implement a really simple model. We're going to take all our US recipes. We have a couple thousand recipes. We're going to filter out, do our data cleaning, get rid of recipes that don't have images, so they're not going to render in the UI. And then we're going to just put these into a simple, similar ingredients and similar name-based model. So if you take the document in this case is a list of ingredients or a list of names, we have these two separate models. We're just lemmatizing those words in those documents, tokenizing, doing some TF-IDF. And we're going to use cosine similarity to come up with a ranked list of the most similar recipes to each of the recipes in our corpus. And we'll pass that through to a post process where we're going to filter out what a member sees based on if there's any dietary restrictions they have, what the course of the recipe they're looking at is. If it's a dinner recipe they're looking at, we think they're looking for dinner, so we only want to recommend to them dinner recipes and other things like that. So how do we get this kind of concept into our Primrose DAG framework? All right, so first, all our data lives in the data lake. So we have our Google BigQuery reader. So if you look up here, we have our first node here, food data, and that is defined down here. So this is kind of the JSON configuration as code structure that we use to create the DAG. So here we have our node food data, and we created a big SQL reader or BigQuery SQL reader class that basically everyone on the team uses to get data from data lake, where we can just pass it the location of the SQL file to read, some parameters to inject into that SQL file if you want to deploy it to production and read production data, or deploy it to QA and read QA only data. Then we have some other parameters we've defined for our reader. And at the bottom here, we have our destination, corpus pipeline. And that's going to be the node that we're going to send the data from the big SQL reader food data node to. So it goes down to corpus pipeline. You can see this name here of the second node, corpus pipeline, is the same as the one at the destination area of food reader. This is a custom class we wrote just for specifically for cleaning up the recipes that are coming from our corpus. We have a bunch of parameters that are pertinent to that process, and then we have destination node. So we have an ingredient model and a name model. So the data object gets sent to both these models, and both those models know that they're looking for something from corpus pipeline because that was in the destination there. We have the code inside these models that's doing the TF-IDF and calculating the cosine similarity of all different recipes, and that gets sent to a post-process node. That's where we have our business logics, like all those filters that I mentioned. So there'll be more JSON there. I'm not going to show all the JSON. But then we can send it out to any number of writers we want. So we write to our Redis cache from which our APIs will read from. And we also have writers to write all our recommendations in a CSV form if we want. We can upload that to Google Cloud buckets if we want. And at the end, it all comes down to the success node where you can kind of have it do whatever you want. Here we're logging a message saying your newbie data scientist has written production quality code. So let's say we want to add on to this model, like we have these simple, similar recipe recommendations, and we want to start looking at building a more complex model that takes into consideration everything a user's been tracking, so the dinner recommendations. So we've already written a lot of code to calculate similar recipes, and we want to add on some things to this model. So now we want to also read member data from our data lake. So we're going to take 2 weeks of tracking history from all our members. Anyone that's tracked more than one recipe is going to be eligible for this recommender. And then we're going to come over here, and basically for everything they tracked, we'll get a list of similar recipes to the item they tracked. So if they tracked an apple, they're going to see similar things would be like a banana and watermelon. If they track pizza, we'll have ham and cheese, etc. And what we're going to do is we're going to apply our business logic. So we don't want to recommend all things related to Apple. So we're going to shuffle this list up. So now we have a mixed order of tracked recipes and their corresponding similar recipes. And we're going to start going down this list and kind of populating the number of recommendations we want to show to the user. So if we have 4 recommendations, we're going to start going down this list. The most similar thing to banana is strawberry. The most similar thing to the salad is salad. It turns out that our member only has like 2 points left, and avocado's like 11 if you eat the whole thing. So we're not going to recommend an avocado. They've already eaten bananas this week, so we're going to skip that. And it turns out they ate like some type of pizza that was vegetarian, and ham's not vegetarian, so we're not going to do that one either. And then we go to the next row, and we got watermelon and salad, and we got our 4 recommendations. So that's kind of in just like how the recommender works. So how do we add all this to our Primrose DAG? So the graph here looks a lot different, but it's really just the same structure. It's just shifted because we've got to plot this extra member node or member data node here. But we're reusing our BigQuery SQL reader here. We're just getting in a different input SQL file, so we're reusing code again. We can tell this reader to send its data directly to this post process here. So it doesn't matter like what order you hook the nodes up in. You can have a reader go right to a post process. You can have a model go back to a pipeline and to another model. It's very customizable. And this is a new post process that we wrote to kind of do this interleaving of recommendations. And then we write to the same writers, and the DAG knows where the data is coming from, and it knows what to write. And then at the end, we go to our success node, and now your data scientist is developing software engineering skills. They're reusing old code and writing stuff to be modular. So we have these 2 DAGs, and we can deploy these pretty easily. So these are both deployed to separate containers. We have our similar recipes DAG and our dinner recommendations DAG. These are run daily. And then they're both running from the data lake, which is updated all the time by our data engineering team. Both these will write to the Redis cache every evening, and then our API is always up and running, and just will read whatever has been written to the Redis cache and kind of serve our various endpoint clients here. So that's kind of a simple implementation of how you can put into production some models in this Primrose DAG framework. All right, so that's kind of the end here. So we have the link to Primrose, which will be coming soon, and I'm sure Carl will send out a link to everyone who attended once it happens. And then, you can also read, we started a tech blog recently. There's, I believe, 2 articles on there now, just started in the last month. I think Carl is another open source tool we have, right? Look ML. So look for a Primrose article in the near future when that's released. And yeah, we'd be happy to take any questions.
When you recommend recipes to users, do you get any feedback from them which recipes they like?
That's a really good question. But right now, actually, we have it exposed and it's going in the front end, but it's all, it hasn't actually been picked up by the users yet. So we basically have it in production, but it's not currently live now. So we'll get back to you.
Yeah.
But in general, we have an event stream. Like we have a recsys social network, so all the comments and likes, they all come to one stream. So that time and get it. Most times it's purely based on sense of like quality or popular.
Yeah, just in this first pass, it's either ingredients or name based. But if we have a different model, we'll just switch out those 2 nodes with whatever we work on, like on the side, and then put those in, and then everything else will flow through, kind of the way it's going right now.
But we do have track counts and the recipe popularity that we can rank and rescore. Like in that second post processing.
And we're also working on several food metadata projects that will kind of, that's kind of the limitation we have right now is really rich metadata surrounding everything, and we're trying to generate that in a way that will make more robust recommendations. It's another project. But a lot of this is really, you got to walk before you can sprint, so we're trying to get something out the door to kind of have a baseline for stuff.
Do any of these nodes, do any of those processes use Spark?
They could, but no, we don't have any Spark jobs right now. Everything's just read in. Like the BigQuery reader does read in like a lot of files in parallel, so it's pretty fast. We can read in 100 gigs in less than a couple minutes or something like that. So hasn't been a huge need for us, but we've done some other projects with like beam jobs as well. And I think that that's kind of the direction that we're going to go internally, but there's nothing stopping it from being a Spark job. Sure.
How would you
So usually we'll have like a completely separate DAG for like training in production, right? But you could easily just have a pre-process that pulls data in from an external source, validates how well it's doing against some KPI if it's a recommender model, or validates how well it's doing against actual data if it's like a model that makes some kind of regression, and then follows a training path if you need to retrain a model, for instance. But it's not implemented explicitly, but nothing stops you from doing that. Sure.
So if the recommendation is purely based on tag similarities,
So it's just TF5 right now.
Oh, did you say tag similarity?
Tag similarity?
Yeah, it's sort of that, but we don't have specific tags beyond like a few different ones that we use for filtering. Most of the information comes purely from the ingredients themselves instead of the tags.
outside, right? The noodle is the main thing, and the salt is a source.
So not right now, but that's what we're kind of working on with like this food hierarchical structure and ontology and understanding like what's the main ingredient in a recipe and what's like a sub ingredient and really breaking down like composite foods into their components. So that's something we're working on now, but that's not in this like simple model we showed today. Yeah.
I'm also working on the quality.
Okay.
Like for counting that you feel there's augmented or some knowledge to know, okay, based on this from a plant and
Mm-hmm. Yeah, we can talk about more about that later for sure, but that's we're trying to automate that process. So
Yeah, so I've actually looked at quite a few like food ontologies. Everyone I find like has really big problems. Or it comes from Europe and it doesn't have like Rocket and Ruby or the same things and have like synonyms across countries. And we have some metadata ourselves, like many I would say this, but it's not complete. So we can't rely on it as a single feature for customers' recommendations, which is why we're looking to XBC and which is now trying to extract that and use some API.
For the classic, sort of recommendation model where you've got your user attributes, you've got your content attribute, you're attempting some sort of factorization from that.
Mm-hmm.
How would you sort of envisage that sort of applying in your pipeline?
So,
because I understand you've sort of got your content features and you've talked a lot about that.
Yeah.
I'm just sort of wondering, what does that pipeline look like when you're actually having to do that process of factorization?
that's a great question. So we have this running for our social media feed right now too. We just A/B tested that, and we run it hourly, and we've got nodes that do like full collaborative filters for the entirety of whatever the posts that have been generated in that last hour are, and then everything's written to caching layers. So granted, there's not instantaneous feedback for that stuff. Like most of the instantaneous feedback has to come from something content-based, but once an hour you will get an updated collaborative filter that comes out of one of those nodes and then is interleaved with our other recommendations and still runs as a batch though. Sure.
Yeah, I had a question about like kind of how it's set up, because you mentioned it's operating like in memory, right? Even between like steps. If you have like one step that's then sending to two different nodes, like how does it, and then one of those nodes maybe is like doing some additional processing over the data, how does it manage to not like run into each other, or are you having to make copies?
You would have to make a copy if you had to manipulate that object in and of itself.
Okay.
But otherwise, I guess you just have to be aware if that's something.
Yeah. But if you don't modify it, then you can just kind of point to it.
Yeah.
Is that how it works?
Yeah, exactly. Yeah, you'd be able to point to the same fundamental object that came upstream. Cool. Thank you guys.
I love how I went quiet at the beginning and there were like 15 questions. So when we set up Yuri, I guess this is time for a quick toilet break, drink break, whatever. Don't do it together, drinking and toilet. Same time, I mean. We'll be back in like 5.